I mentioned that the system is trailer mounted, so we can do over the highway demonstrations. Just last week on Tuesday, we were up at Wilsonville, just south of Birmingham. They have Alabama Power has a coal gasification plant there, and they were doing engineering day for their students, and they invited us to come up and just be one of the the demos for their day. They had some electric vehicles out there, and so we do a lot of those kind of events. We've traveled about 23,000 miles. But the other benefit of this system is we've used it for research. We've had 2 graduate students do their master's work on it, and we have a third who's getting ready to start, where I can sort of carve out the time to get him started. Our first graduate student, his graduate project was to look at different regionally available feedstocks and analyze the syngas coming off and see if it varied from one feedstock to the next, and see how well we could convert the material. And that was the first project, so it was a learning curve for the student as well, but it was also a learning curve for me on how to operate the system. The system is completely self-contained. In the front, behind the plexiglass here, we have 2 bins where we store our biomass. The biomass will be fed out of the bin into the sorting screen. And the sorting screen, all it's going to do is sit here and shake. And when it shakes, it's going to sort out the real fine particles, so something more like sawdust, and the real large particles, and it's going to keep just the wood chip, something along these lines is what it's going to let through. And that's a fairly uniform, for us, it's fairly uniform size material that will then go up the vertical auger here into the top of the gasifier. Our gasifier, this one's an open top downdraft system, so the biomass comes in the top, it's open to the atmosphere, so it's not pressurized. The biomass comes in, and it gets, as it gasifies, it moves down. All the gases are pulled down. Temperatures in here are between about 17 and 1800 degrees Fahrenheit. So as the wood chip enters the top, it gets broken down and converted to a gas. By the time it hits the very bottom of the gasifier here, it's completely converted to a gas. Think about pouring pellets through here. We don't want them flowing through too fast to the point where we're ending up with cold pellets in the bottom. But first of all, it's an inefficient system. You end up with a lot of extra carbon you don't convert. But second of all, if you don't completely break down that material, you end up with a lot of tars. And when you end up with a lot of tars, and you start tarring up the system, whether you tar your heat exchanger, tar your filters, and you're trying to break down the tar. One of the nice things about downdraft gasifiers is they break down tars really well. So that's what I'm saying is the nice thing about gasification is it can handle a wide variety of materials, but you got to make sure you're set up to handle each one individually. So a little bit on some of the different biomasses. These are all 3 different kinds of pellets here. Clean pine chips is what's in that drum, that bucket in the middle one. And this is just pine that we got from the chip and saw plant in Opelika. These are whole pine trees that come into the plant. They run up through a delimber, a debarker, and it's just a clean pine material, and it's chipped up. Some of the chips we've made in the field, clean microchips, which is what sort of spilled out over here. These are chips that were, the trees were delimbed and debarked in the woods and then chipped in the woods. So one thing you notice is they're smaller because we call them microchip. But if you really start to look closely, you'll see there's more dirt and bark and other stuff in here. Just when you do the in-woods operation, it's not going to be as clean as you do it at the mill.
And Christian, can the gasifier handle that dirt?
Yes, it can. That's where I'm going with this. Clean whole tree microchips is going to be the whole tree, something like that, but bigger. Bark, limbs, needles, everything goes to the chipper, straight to the chip truck. And that's what we have here. These are microchips. And as I mentioned earlier, clean pine chips from what we get from like the chip and saw plant, 0.5% ash, more or less. When you go to a whole tree, you're looking somewhere in the vicinity of about maybe 2%. And a lot of that we're learning depends on how the tree is felled and skidded to the landing, what your soil conditions are. Because if you skid a tree and it's real muddy, you're going to have more dirt that sticks to more soil that sticks to the tree and bark. And when you chip that goes in there with it, and that raises your ash content. But yeah, we can handle 2%, no problem. We start going to switchgrass, this is a pelletized switchgrass. This is going to be about, these came from out of Tennessee with Genera Energy, and just a regular pellet. This is about 4% ash content, so we can still do that. We can still do 4%. The last tub I have over there with the lid on it is poultry litter. I think you guys all know what I mean when I say poultry litter. If you get a whiff of that, you'll learn real quick. That's about 25% ash content. That we can't handle. The issue with ashes is when we put material that has ash in here, ash won't convert. It's going to stay as ash. And what happens with ashes, it's going to agglomerate. It's going to fuse together and create these big, what we call clinkers. So we'll get some clinkers that form. And these obviously aren't going to make it through as gas. They're going to stay like that.
Pass it around.
Yep, and that's primarily ash. And there's going to be some carbon in there from, and actually that was from switchgrass belt. So we're a little surprised to see that.
Okay. So there's another term that we've used in class is slagging.
Okay.
So it's slag.
Yep.
Looks almost like volcano larvae.
It does. It does. And when you get to certain temperatures, it actually starts to form some really sort of fairly brittle but shiny material. It's a little bit, it's neat looking. So, but that's what happens when you get too high of ash. That's what happens to it.
And you don't want that.
Yeah.
It's a lot of work to clean it out.
As I mentioned, this is a downdraft system. We don't like clogging. Well, that's going to cause clogging, and eventually what's going to happen is you're going to completely clog it up. We can't get your air gas through. And the way we know that's happened is we measure differential pressure. So we know we're at non-pressurized, so atmospheric pressure top. We look at how hard we're having to pull to get the gas through, and if it's really high, then we know we've got something going on in there. And usually, you find out, you'll see stuff like this. If you know you've been running high ash content material, or you'll just get a lot of fines that just build up, just real fine particles. Any questions on this system?
Condensation. Do you have any condensation or taking off condensation anywhere?
If we're operating like we want to, no. When we start the system up in the morning, in our filters we have some heaters that'll preheat our filters. We'll preheat our heat exchanger, get everything above about 110 degrees Fahrenheit. 40 C is what we go by. And once we get above that, we'll start pulling our gas through, igniting our char, and by keeping everything warm, hopefully we're not condensing any gases. Now on a really cold day, we may not be able to hit some of those temperatures, and we'll start running and pull our gas through, and then we will get condensation. If we get condensation, we're probably going to condense tars, and it's going to gum it up and shut us down. So if everything's operating like we should, no. Anybody else have any questions?
When you're swapping your feedstocks, you were saying, is that just you have to let LabView know to change your oxygen you're pulling through it?
Well, yes and no. We'll let LabView know we're swapping, but it's not our oxygen we change. This is an air blowing system, so we're going to blow about the same amount of air. We will change up how much air we're injecting at each level and our target temperature at each level in LabView. But the biggest, so that's important to change that. And that changes from whether it be you're going from wood to, like, say, a pecan shell or a walnut shell to a pellet. So it depends on your biomass. You're going to change up how much air you're injecting. But the big thing you change is we have a vibrator on here, this little orange cylinder, and it shakes the whole system. And that's what flows our material through the gasifier. We have a grate shaker down here. It just moves the bed to break up any clumps. And we got to change the settings on those. And the reason it's tricky is because when we put biomass in the top, that biomass is going to stay in this gasifier for about anywhere from 4 to 8 hours. So it's going to be in there for a while. So we can't just start feeding pellets and say, all right, let's change this setting from going off every 45 seconds to going off every 300 seconds and you're done. But you still have mostly chips in there. So you guys sort of easily slowly transition it and watch your differential pressures and make sure you're not going too high or too low. Or too low is usually not an issue, but too high. So you guys slowly transition. So, and it'll take you about 2, 3 to 4 hours to completely switch over. Once you switched over, then just let it be on about its business. The settings are in there, but it kind of like along on its own. So
you mentioned the KW, and you translate that horsepower. I understand horsepower like that and do. About how much horsepower would you be maintaining?
I'm not really sure how much horsepower we're generating. I think those Chevy engines are about a 190 horsepower on gasoline. Now you're going to have to reduce that horsepower down on syngas. I can't.
24. KW. It takes about what, 2 horsepower to make a KW? Some.
No, I don't have those numbers in my head. Yeah, we could do some, quick conversions on there. So the genset on this system is a on-demand genset, so it's only going to generate the electricity that we are asking of it. As I mentioned, our system uses about 1 kilowatt to keep itself going. When we put a load up, it's going to step the load, it's going to step up the generator. So what happens is we maintain a gas flow rate through the system, and as the engine needs more gas, it's going to pull more gas. If it doesn't need that gas, that gas is going to go right past the engine, out its flare. We have a flare stack on the roof, and we'll flare the gas. We flare it because of the carbon monoxide in there. Go ahead and burn that off. But so when we're running our engine at low loads, low kilowatt loads, we're fairly inefficient because we're flaring a lot of gas. We're generating the gas, making the gas, but we're not using the gas. So we're just burning it for no purpose. So your most efficient is to run at high loads on this type of system. How are we doing on time?
We're okay. We're flexible.
Okay,
Yeah.
okay. I don't want to keep you guys too long and save enough time to go inside. So, one of the
I figured
I was gonna say 1 kilowatt is 1.34 horsepower.
okay.
So it's not a whole lot of difference.
Now about 60 horsepower.
Well, is that kilowatt electric kilowatts?
I just typed in kilowatts
Okay.
to horsepower on Google.
Yeah. We looked at switchgrass pellets. We looked at clean pine chips. We looked at hardwood pellets. We looked at peanut hulls and poultry litter. Those are I think the 5 feedstocks we looked at. And poultry litter, I've already talked a little bit about the ash content and what we saw with it, so we'll leave that alone. We had trouble, so we weren't able to, do the poultry litter on this project. But from the other 4 feedstocks we looked at, the surprising finding for us was all the syngas looked the same. We didn't see any statistical significant differences in the feedstock. There were small differences, but they weren't significant. So that was a bit surprising. That I guess which leads to one of the benefits of gasification is it doesn't really matter what kind of feedstock you can provide. Your gas coming out is going to be fairly uniform. You're going to have those numbers I told you earlier, about 20% CO, 20% hydrogen, and 10% carbon dioxide.
How did the peanut hulls go? Did they handle okay, or did you have to pelletize
They
them?
were pelletized as well.
Okay.
I think now we have more experience, and we could probably handle raw peanut hulls now and be okay, but early on we're just trying to be sort of conservative with some of our testing.
See, the problem with peanut hulls is they're so light. The
Yep.
bulk density is extremely low, and that can cause problems in a system like this. You need it to flow, but if you can get to equipment that can handle something without pelletization, you're ahead of the game, because
Right.
pelletization costs. Okay, it costs money to do that.
I completely agree. We can use the pellets. We don't like to because they're expensive and their energy. It takes a lot of energy to make a pellet, so we prefer going with the chips or something like that. Some of the other work we've done. Our second graduate student finished there. His whole project was poultry litter, seeing if he could work with poultry litter. This was Ryan Haynes, you know him, to make it work. And we tried all sorts of stuff. We tried lowering our temperature in the gasifier so we were below the ash fusion temperature. We tried mixing with wood chips. We tried pelletize. We tried raw poultry. We tried mixing with lime. That's supposed to raise the ash fusion temperature. And we were able to get it to work somewhat, but never to where I'd be comfortable just letting it run 24/7 like that. And then just some of the other work we've done. We've tried some other materials. We've tried pecan shells. A lot of pecans here in Alabama. We've tried regular yard waste, just the limbs and everything.
What did you think of the pecan shells?
Pecan shells were great. Really liked them. So the one challenge with pecan shells is most of the people, the processing facilities for pecans, they shell the pecans and then they immediately grind the shells. So you gotta get them before they get ground.
Yeah.
Once they're ground, they're too fine for us. But we worked with Priesters and they got us 2 huge sacks. I mean, I'm talking 4 huge sacks. These sacks, 1,000 pounds each, and they work great. The nice thing is there's a little bit of residual oil from the nut left in there, and it sort of raises the energy content of the shell. So they work great.
Is the reason you pelletize material to increase the bulk density?
Yeah, you get more energy in a smaller space. So,
But as well as surely as well as to make sure you got the downdraft, you've got to have particles that have gaps between them.
Pelletization is going to make your material more uniform. Anytime you work with biomass, one of your issues is non-uniformity. Yeah. It's going to make it
For
more
example, Christian, you couldn't put sawdust in here, loose.
No.
So that you have to particulate it. Yeah.
So on the hardwood, yeah, we could chip it and use it, and we've done that. We've run sweet gum or whatever scrub oaks we can get. But a lot of the pellets, they're exported to Europe, so we just sort of grab some and test with them.
Yeah.
So, but yeah, your feedstock has to be in a pellet or a chip, some sort of a solid that's going to be able to move through and slowly gasify.
With the ash or char that's removed after the gasification, do you have any use for it, or how do you dispose of it? Or
We currently we don't have any use for it. I know there's been some study of doing some studies, or some talk about doing some studies using it for fertilizer and stuff like that. We haven't really done much with it. We don't get very much. This system does convert pretty efficiently. We did a test where we gasified right at about 3,600 pounds of biomass, and we ended up with 16 pounds of char. So there's not much left over. Currently, we bag it and just landfill it. We're talking about small bags, so it's not much. The issue I think you'll run into pretty quick if you try to use it as a fertilizer is this material is really fine. I mean, you've worked with gasification, it's really fine. So just a little bit of wind and it goes air blown, and you have the same issues you have with coal miners. It's the black lung disease. You really be careful when you're handling it to not breathe it in. You got to wear the right respiratory gear. So that's the one issue you have to be careful with.
Any other questions?
If we have a few minutes, we'll stick our head inside and see the other guys.
One from me, and I know you've told, but I want them to hear this. Capital costs of this. Did you say 25 kilowatts?
25 kilowatt. Yes. So this system is Community Power Corporation. They build their systems. Their idea originally their idea was power for communities that don't have electricity. So go into a small community, put in a 25 kW gen set, and they can use some sort of feedstock that they may have there in their area during electricity. But what happens is that if you're a community that can't afford electricity, you probably can't afford one of these either. So the capital cost, if you were to go buy, and they still make these, if you were to go buy a 25 kW system, it's going to cost you about $250,000. So that's a lot. When we first started doing some of this research with this, we thought this might be a good way for distributed power generation. So not so much for communities that don't have power, but just put these around. You can power generate electricity. But you realize real quick that you run the economics of it. The best case scenario, that's if everything lines up perfectly, you're looking at about 30 cents a kilowatt. If you're looking at your power bill, you're probably paying 14 cents a kilowatt after taxes. So it's just there's a reason why when Southern Company puts in a power plant, it's a gigawatt or whatever. It's capital, economies of scale.
that doesn't include the truck, does it?
No sir. No sir.
Okay, I didn't know. A nice looking truck.
That doesn't include the trailer. That's just the gasifier. That's everything you see inside this yellow box here. So Community Power Corporation's vision is for these to sit on the skid behind your building. Now they've actually started putting them in shipping containers like this, 20-foot shipping containers. So
So that don't include this up here.
No, that includes everything everything except for the trailer. So everything you can set, you can put it inside a shipping container and sit behind your building. So, yes, sir.
And Christian, how will that
They just about 2 years ago they got bought out by a company called Afghan. Can't remember the rest of it. They're doing okay. They've started developing 100 kW systems, and it's a very niche market they have. So a lot of that market is Department of Defense and research groups. So there is one of these. I will mention there's one of these that is in operation by a commercial entity. It's a walnut processing facility in California runs one, and they originally bought a 50 kilowatt system, and they were using the walnut shells to gasify those, and they had a big they had a big need for electricity as well as heat. Both these systems generate electricity and heat, or you get a lot of that. So they used it, and I know just last year they purchased a second unit, a 100 kW unit, so they must really see a benefit. Now, I'm not sure if maybe they have some renewable energy incentives, where they're sitting that lets them recoup some of their costs or not. But a 100 kilowatt system is going to cost about $1 million. So there must be something that there must be something that's helping them out.
Well, too, the retail price of electricity in California is way higher than it is here. Okay, so that would help too, if they're saving that.
Yep. Any more questions? If we have a few minutes, we'll just stick our head inside and show you a different kind of gasifier, and we'll be done. The biomass will be fed out of the bin, into the sorting screen. And the sorting screen, all it's going to do is sit here and shake. And when it shakes, it's going to sort out the real fine particles, so something more like sawdust, and the real large particles, and it's going to keep just the wood chip, something along these lines is what it's going to let through. And that's a fairly uniform, for us, it's fairly uniform size material that will then go up the vertical auger here into the top of the gasifier. Our gasifier, this one's an open top downdraft system, so the biomass comes in the top, it's open to the atmosphere, so it's not pressurized. The biomass comes in and it gets, as it gasifies, it moves down, all the gases are pulled down. Temperatures in here are between about 17 and 1800 degrees Fahrenheit. So as the wood chip enters the top, it gets broken down and converted to a gas. By the time it hits the very bottom of the gasifier here, it's completely converted to a gas. Carbon monoxide, hydrogen are our two main gases. Then carbon dioxide, a little bit of methane, a lot of nitrogen, and a little bit of oxygen. The gas comes off fairly warm. It goes through this stainless steel area here, which is just a pipe with a lot of insulation around it, to the back side of our trailer, which is our heat exchanger. You want to walk around back there and take a look at it, or just you're okay? The heat exchanger is that stainless steel tube you see way in the back there, about 14 inches in diameter, and that's just going to take our syngas and cool it from 1400 degrees down to about 200 degrees Fahrenheit. After the heat exchanger, we go into our filter box, and this is a cold gas filtration. The other gasifier we talked about inside is warm gas filtration. So at this point, we're filtering the gas at around about 120 degrees Fahrenheit. The gas gets filtered, and we're just removing particulates, ash and char. We're not doing any scrubbing or anything like that. The gas comes out of the top of the filter box and goes into our engine compartment in the back of the trailer, where it runs into an engine, and then that engine turns a generator to give our final product on here, which is electricity. Our genset is rated at 25 kilowatts electric, and the system itself uses about 1 kilowatt to keep itself going. And what you're seeing now is our small control room, where as an operator you sit with a laptop and maintain the system.